Hello. Okay, I want today to try to explain two very important concepts from quantum mechanics applied in the quantum computer. Okay, and that video is for you who is young. I think science have to go to the young kids to they be able to already get like the concept. In the future, they are gonna have to be able to probably work with quantum computer. And I think quantum mechanics start getting like more and more our day topic. Right? Then as a quantum physicist, I think two concepts we can try to explain. And the quantum physicist is not a very good magician, then sorry for the mistakes in my magic. But I'm gonna use magic to explain those two phenomena. Right? Recently, I started to work with quantum computation. It's very amazing, like using Qiskit with Python. It's very cool, very easy to go on. But I'm noticing it's better if you master those two concepts of quantum mechanics that we're going to explain is the superposition of states and the entanglement state. Okay, to do that, at the superposition, we probably already heard about like the Schrödinger's cat. Probably his name, I pronounced it wrong, sorry. It's like he proposed like a mental experiment when you can put a little cat inside of a box together with something who can kill the cat. But the odds of the cat get killed is like 50%. What it means is, once you close the box, you do not know if the cat is alive or dead. The only way to know it if you open the box. The act of opening the box is doing the measurement. Alright? And the fact that you do not know, it means the cat is in a superposition of state. Dead or alive. It means he's not dead or alive. You do not know. He's in the both. Right? But as I present this for kids, for example, I'm gonna try to present that for my daughter's birthday party. That's like our practice run. Okay, sorry then if I do any mistake. You can give me feedback how I can improve. I don't want to say the cat's dead, because if I open the box, like the little kids are gonna get very, very sad. I get sad as well if the cat's dead when I do the experiment. Then my daughter also helped me to build that box. That box is a special box because it's a teletransport machine as well. Then once I close this box, the cat can get teletransport with the odds of 50% as well. Because I'm not very good experimentalist, I found out that. And then the cat not always gonna get teletransported. The box is not gonna work always. Okay? And then that's why I do have this cup here. Okay? Because this cup is where the cat is gonna appear. It's like they can appear here or not appear here. That is like the very important concept we are gonna go, because we're gonna use the teletransport machine and the cup to be able to explain if the cat is here or not, and if those two objects are entangled. That is the idea behind my quantum simulation. Just stopped running, look like. Good. And the computer went wide. And then here, back to the experiment. Once I close them, I close that box. Right? I close the box. Then I do not know if the cat is inside or not. The only way to know that if I open that box again. But I know also there is another information here in that game is the cat can be here. Because it could work. If it work, the cat is gonna be here. But if I don't open this, I do not know as well. Then now we have like a superposition of states. Here or not here, and here or not here, right? But those two objects are entangled, right? What it means is, if I measure that object here, I automatically know what is inside of that box. And if I measure that object, I automatically know what is inside of that cup. Wow. But then that's why it becomes some paradox, right? It's known as like DPR, like Einstein-Podolsky-Rose paradox. I hope I get the names correct. Probably not. I'm very bad with names. That should not work. Is that because how now? Because at the moment it's in a superposition. Then the cat is not here and here at the same time, correct? I do not know. But then if I do the measurement, that state needs to know exactly what happened in exactly the same moment. And that means that in one moment, these guys have to change information to be able to say, hey, you have to be there because the measurement happened here. Then that's why it's a paradox, because in the relativity, nothing can go faster than the speed of light. But that information went. Because if I move this one, like for example, like far, and move this one like far away, and then do the experiment. I don't want to take off the camera because otherwise I'm going to think the trick is that. Damn it, no, that's not the trick. Then I do not know. It's happening, it's a quantum thing is happening here. Then I do have to measure first. But the idea is that's in a superposition of states, in or not. All right? The cat is inside or not. That's the superposition. Like in the Schrödinger's cat is dead or alive. And those choose an entanglement. Because the moment I know that one here, I know automatically what is the other one. But when I do not make any measurement, I do not know it. Then let's measure. Let's measure first the box here. Let's measure first that one here. Yeah. Because that one I can open like very slowly in the camera here. Let's open very slowly in the camera. And see if the cat's here. Can be here. If you hear that, it's not there. But if not here, it's there. The cat was in the middle. Oh, yes. The cat is not here. Then I already know the cat have to be here. Yes. As we know, the cat is there. Meow. And that, I hope, could help you a little bit more to like understand those two concepts. Yeah, but those are weird, they are weird, but that's the world. Then let's use that for doing good thing. Have fun coding in a quantum computer.